In section 4.3, we are learning how to determine whether a function has absolute extrema. So similar to relative mins or maxes, we know that a function can have an absolute min or max on a closed interval. So the extreme value theorem tells us that if a function is continuous on a closed interval, then it will attain both a minimum and maximum value. So just a reminder that the minimum and maximum can be, but don't have to be, a relative min or max. So in figure 1, if we were to look at this function on this closed interval from whatever our x value is down here, some a value and some b value, well, the maximum, the absolute maximum, would just be the greatest y value, so the greatest output on that interval. So remember, the maximum itself is the y value, so like 4 point something, but it occurs at the location of this x value. And in this example, the minimum value would be the relative minimum. So that is both the abs minimum on that interval, and it's a relative minimum of the function. So similarly, in figure 2, if we just look at the same function, but we consider a different interval, so different a and b values, well, this time the maximum value, the absolute maximum on that interval, is also a relative max of the function, but the minimum value is not. So the minimum value is an endpoint of the interval. So again, that's the absolute minimum from some x value a to some x value b. And again, the minimum is actually the y value. Same with the maximum. The location will be x values. And so we know this one would be located at one of our critical values, not an endpoint of the interval. Lastly, when we consider the entire function, in this case, in figure 3, this would have no absolute or absolute min or absolute max because the function continues down forever and up forever. So we could identify relative extrema, but there'd be no absolute min or max if we consider the entire function. When we have even though, like so an even polynomial or power function, I could say, so I drew these graphs on here, the function x squared minus 5, it's going to have an absolute minimum value. So even if we don't consider a closed interval, in this case, the relative minimum would be the absolute minimum of the function, but there would be no absolute max. Oops, no abs max. Down here, if our function's concave down, this would have an absolute maximum value. It would be the same as our relative max, but no absolute minimum. So most often we will look for an absolute min or max on a closed interval, but occasionally we might be asked about the minimum value of a function like this. So we just have to reason that we have to kind of just think about what the graph of the function looks like. All right, so I'm not going to read the text on this page, but you should definitely read the text on this page. So in general, for this lesson, we want to consider that absolute extrema can happen either at the endpoint of an interval or at the location of a relative max or min. So as I work through these examples, I'm going to model them the way we would be expected to show our work for a free response question. So in the first example, we're asked to find the maximum value of f on the closed interval from 0 to 3. So absence of the word relative, when we are just asked to find the maximum value, the implication there is that it's an absolute maximum value. So this is going to start off very similar to what we did looking for relative extrema. I need to consider the endpoints of the interval, so 0 and 3, And I need to consider the critical values. So first thing, we're going to find the derivative. All right, I know I've got to use the chain rule here because I have the sine of x squared. So I know my derivative is cosine of the junk, x squared, times the derivative of the junk. So we could write our derivative 2x times the cosine of x squared. All right, our second step is to find the critical values. So again, this hasn't changed. I know that f prime is never undefined since it is a cosine function, and x squared is never undefined, 2x is never undefined, and the cosine of anything is never undefined. We know our cosine function looks like our sine function. It's a sinusoidal curve. All right, so I'm going to set f prime equal to 0, and this is already in what we would call factored form because, well, there's no other way to write it. It's a factor 2x times a factor cosine of x squared. So I can use the zero product property to see that one of my critical values occurs at 0. And then I need to consider where the cosine of x squared equals 0 on this interval. So on this interval, remember, these are values of x. So we're considering values of x that are less than or equal to 3 and greater than or equal to 0. But since this is x squared in our cosine function, what I like to do is transform this interval. So if I square everything, and I know 0 squared is 0, 3 squared is 9. If I square everything on the interval, I can now consider this interval when I go to the unit circle. So the only thing I can do mathematically to this equation here is I can take the inverse cosine of both sides, or the arc cosine. But one way or another, I have to go to the unit circle. And I know that 0 and 9 are not values like in radians that I usually consider on the unit circle. So I just have to think about them a lot. I know pi is about 3.14. So I need to consider that when I'm going to my unit circle. All right, so if I start at 0, I know that the first time my cosine value is 0 is going to be up here at the top of the unit circle at pi over 2. And I know pi divided by 2 is on the interval from 0 to 9, since pi is 3 and some change. So I could get that x squared equals pi over 2. All right, then the next time that I have a cosine value of 0 is at, well, 3 pi over 2. All right, as I come around the unit circle, I'm now back here at 2 pi, and I know that's still on the interval from 0 to 9, because 2 times pi is going to be like 6.2 and some change. So as I come up here, I get another value. So we said, what, that's 3 pi over 2, 4 pi over 2, 5 pi over 2. And that's still going to be on the interval from 0 to 9. And then let's see, if I come around to this axis on the unit circle, that is now going to be 3 pi. And 3 times pi, I know, is a number that is greater than 9, because 3 times 3 is 9, pi is a little bit more than 9. So using that reasoning, I know that 5 pi over 2 is the last time on the interval from 0 to 9 that I get a cosine value of 0. All right, so lastly, I want to know the values of x, not x squared, so I just take the square root of everything. So the square root of pi over 2, the square root of 3 pi over 2, the square root of 5 pi over 2, and remember, those are all positive. not because they couldn't have negative solutions. Normally, solving x squared equals pi over 2, for example, I'd consider the positive and negative, but because the negative values won't be greater than 0. And again, we're looking at this interval from 0 to 9 for x squared, in this interval from 0 to 3 for values of x. So those are the 3 critical values that we get. And then in addition to that, we had the critical value x equals 0. But since x equals 0 was already the end point of our interval, we were going to consider it either way. So here's where the process for finding an absolute min or max is different from a relative min or max. Instead of making a number line, we're going to make a table of values, because the number line is only good for testing like the signs of the derivative, but we need to know if when x is 0 or if x is 3, if that value is greater or less than our critical values. So we're going to make a table. All right, so in my table, I want values for x, and I'm plugging these into the function itself, not the derivative. So that's another thing that's different from our number line. So I'm going to consider 0, the square root of pi over 2, the square root of 3 pi over 2, the square root of 5 pi over 2, as well as 3. So in our table, we've got to include the endpoints of our intervals, or interval. So these values, the 0 and the 3, and we've got to include our other critical values. All right, now we just plug these into the function itself and see what gives us the least and the greatest value. So I would encourage you to just kind of do this work out to the side. So the sine of 0 squared is just the sine of 0, which is 0. When I get to, the square root of pi over 2, I don't know why I wrote a 0 there again. When I plug that in, well, the sine of the square root of pi over 2 squared is just the sine of pi over 2, right? Because squaring the square root of pi over 2 just makes pi over 2. So on my unit circle, I know the sine value at pi over 2 is positive 1. So then when I consider the square root of 3 pi over 2, when I plug that into my function, that just becomes the sine of 3 pi over 2, since I'm squaring the square root, because remember my function had x squared in it. So the sine of 3 pi over 2 is negative 1. And then lastly, when I find this, the function value of the square root of 5 pi over 2, I just plug that in to my function. That becomes the sine of 5 pi over 2, since I'm squaring the square root. That's going to give me another positive 1. Now, I don't expect you to know what the sine of 3 is, or rather 3 squared. So when I plug in 3, I get the sine of 3 squared. And in my table, I'm just going to write that that is the sine of 9. But if I think about in my unit circle, where 9 would be, we said we know 3 times pi is 3 times 3.1415926, and so on. So I know that 3 times that number is a little bit more than 9. So who knows, this, like 9 in radians would be over here-ish. It would be before we get to 3 pi on the unit circle, but after we pass 5 pi over 2. So we have to use a little number sense. But in our table, all we really need to do here is write that this would be the sine of 9. And again, I don't expect you to know what that number is. I don't know what that number is without a calculator. But what I do need you to realize is that number is less than 1, because only at the top of my unit circle am I at positive 1. We know the axes, sign of anything on the axis would be 0, because sign is our y value. So if I'm on the x-axis, y is 0. And I know at the bottom of my unit circle, the sign value is negative 1. So I don't need to know the sign of 9 to know that it's neither the min nor the max. So we find out that the absolute max is 1 and the absolute minimum value is negative 1. All right, I didn't leave a lot of space for myself to answer this question, so I'm going to delete my side work, but if you already wrote this out, maybe you could just kind of, I don't know, write small or write out to the side, or maybe you left more space for yourself. But our last step is to answer the question, and I would not, I don't think labeling the table is sufficient, but I will say that the table does count towards our justification of why we know we have an abs max value of 1 and negative 1, whereas like a number line isn't something that's usually scored on the AP exam, but we still use number lines to help us find relative extrema. So we could say the maximum value, and in absence of the word relative or local, the implication is that it's absolute or global. So the maximum value of f, or f of x, on the closed interval from 0 to 3 is 1, and we could say that this occurs at x equals the square root of pi over 2 and at x equals the square root of 5 pi over 2. And then similarly, we could say the minimum value of the function f on the closed interval from 0 to 3 is negative 1, and this occurs at, oops, that's not the word at, this occurs at x equals the square root of 3 pi over 2. So we need to make a table here because we're not considering like, we're not using test points to just find a relative extrema, but the table helps us also consider the endpoints. And we want to know the actual values at our critical values. So we want to actually evaluate f, which is not something we have to do when we're finding relative extrema unless we're asked for the actual relative min or max value. So the work here, I'd say step 4 is answer the question. The work here should earn us all the points on a question like this. All right, I'm going to make the next examples in another video.